Alright, welcome back. In this video, we're going to go over how to control blood pressure. There are many ways that your body can actually control blood pressure. This is the use without medication. We're going to go over 2 out of the 4 mechanisms. The reason is because mechanism 3 and 4 use the renal system mainly. So it's not really important now. It'll be more beneficial that you learn it in the renal system, which is the next topic. So the 4 mechanisms are using baroreceptors. That's number 1. Number 2 is using chemoreceptors. Number 3 is E.M.T or acyl natriuretic peptide. And 4 is renin-angiotensin-aldosterone mechanism, which is by far my favorite mechanism in the entire body. It is so fun to teach, probably my favorite topic ever in physiology. It's just really interesting on how it works. And in that mechanism, there's an enzyme that gets made. But that enzyme is made in a very interesting place. You would never be able to guess it. So we're going to get to that when we get to it. But let me tell you a story first. This is going to be a really interesting story which has to do with this. Back when I was in physiology class, this was probably about 5 years ago now, we had to do a lab. This lab involved a bucket of ice water. So what we were supposed to do is we were supposed to submerge our heads into this bucket of ice and hold our breath. You're supposed to hold it as for long as you can. The goal was about a minute. And what we were supposed to do is after that minute, you would take our heads out and measure our respiration rate and our heart rate and see what would happen. Why is this important? This is important because it has to do with chemoreceptors. It is essentially your body's life support system. It is really interesting. So keep this story in mind, what I just said, and think to yourself, what should happen? What would happen to the respiration rate and your heart rate? So before we do that, let's do baroreceptors. Baroreceptors are specialized sensors that detect blood pressure changes in your body. When you go turn on the TV and you're watching the news or the weather channel, and they're going over the weather, sometimes the meteorologist will say, oh, you have a high pressure or low pressure system. How are they measuring that? Well, they're using a barometer to measure that. It's a device that measures pressure. This is basically the exact same thing in your body. It's called a baroreceptor. It measures pressure. So where is it found? When you take a physiology course, they just mention baroreceptors and you just assume it's everywhere in the body. This is not true. It's actually located in very specific places. One of those places is in the aortic arc, right here. Your aorta has a slight arc to it. In that arc is where the baroreceptors are located. It's also located in the carotid sinus, which is not in this picture. But don't worry about these. Don't worry about this. This is not an anatomy class. This is physiology, so you don't really need to know that. So let's go over the mechanism. What's going on here? The first thing is obviously when blood pressure increases, because this mechanism wouldn't have any involvement if the blood pressure was low or normal. The first thing is blood pressure increases. What's going to happen is the baroreceptors are going to detect this. They're like, uh-oh, high blood pressure. And they're going to start firing action potentials. It's going to fire action potentials and the signal is going to go somewhere. Well, it's going to go to their brain called the medullary cardiovascular center, which is located here in the brainstem. It's this little purple thing right here. That's not the important part. What's the important part is what happens afterwards. There are a few things that's going to happen. The first thing we're going to do is we're going to decrease the sympathetic response in the heart, arteries, and veins. So we're going to try to decrease his heart rate. We don't want the heart rate to be high, because if the heart rate is high, that's just going to increase blood pressure even more. And that could be deadly. So the goal is trying to reduce the heart rate. So we're going to decrease the sympathetic response. Because remember, the sympathetic response uses epinephrine, norepinephrine to increase heart rate. Well, we don't want that to happen. So we're going to basically silence that system. We're like, shut off. It doesn't technically completely shut off. It is always on, but we're just lowering it by like 90%. We're also going to vasodilate our blood vessels. Because the bigger the blood vessels, lower the pressure. Imagine if you have a water bottle, an empty water bottle, and you squeeze it so it's all like crinkly. Then you try to fill it with water. You can't really get much in there. There's going to be a lot of pressure in there, pressure buildup, and you can't get much water in there. But if you were to expand that bottle and make it back to this regular size, the pressure can go back to normal. Well, we're going to decrease the pressure, and we can get more blood in there. And that's what we're trying to do here. Think about the blood vessels as a water bottle. So to decrease the pressure, we're going to vasodilate. At the same time, we're going to increase the parasympathetic response to the heart. So we're going to use acetylcholine to reduce the heart rate. Because the acetylcholine is used to decrease heart rate. And all this together is enough to decrease the blood pressure. Well, it should be, hopefully, enough to decrease blood pressure. And that's how baroreceptors work. So all we're doing is decreasing heart rate and vasodilating. That's basically what we're doing. Now for chemoreceptors. These are specialized receptors that detect chemicals, ions, and molecules, like O2 and CO2. Chemoreceptors are located basically in the exact same place as baroreceptors. This is a different picture. In the aortic arch and in the carotid sinus. This is how it works. It's quite interesting. So if the chemoreceptors detect a low O2 concentration or a low pH or a high CO2, we're going to activate the sympathetic system. Why? Okay, let's go over slowly what's happening here. Let's just say if you have a low pH. Start with low pH. If you have a low pH, we have a high ion proton concentration here. Because remember, in a low pH, higher protons, more number of protons. If you have a high number of protons, this is actually causing higher CO2 levels. If you have high CO2 levels, this can cause acidosis. Your blood is too acidic. This can be deadly, very deadly. Why? You probably learned about something called proteins denaturing. One of the ways they can denature is by low pH or acid. Your brain is made up of proteins. Your entire body is made up of proteins. So you have a technically, if you have a low pH blood or acidosis, that blood will eventually get to the brain and cause destruction. It will cause proteins to denature. You can become, go into a coma. You can die, like really fast. So what is your body going to do about this? Your body's very smart. It knows what to do. What your body's going to say is that, okay, we need to really quickly increase heart rate and increase respiration rate. Why? The goal is to pump out all this CO2 we have in our body really fast. So you're going to hyperventilate. Our goal is to get that CO2 out of our body as quickly as possible and get more oxygen in so we can survive. This is basically your life and death mechanism right here. Your life support system. So you're going to start breathing fast. Well, if you breathe fast, we need to get more blood over to the lungs to pick up more oxygen and deliver it to our tissues. But how do you do that? We need to increase our heart rate so we get more blood getting to our lungs to pick up oxygen. Because just imagine if we're getting oxygen into our lungs, but our heart rate's still the same. There's just going to be oxygen just waiting in our lungs, waiting to be picked up. And that's a bad thing. We're waiting on our heart. So we're going to increase our heart rate as well. Because our goal is to exhale that CO2 and get more oxygen in. At the same time, when you exhale that CO2, we're losing proton concentration. So we're going back to our proper pH. So back to my story back in physiology class. We dunked our heads in that ice water, lifted it up after a minute, and we noticed a higher heart rate or respiration rate. Exactly what we have here. Because we were building up CO2 in our lungs. When we hold our breath underwater, we already did that gas exchange immediately, right? We exchanged in that first few seconds, we did that gas exchange from oxygen to CO2. Now there's CO2 in our blood and in our lungs just waiting to be exhaled. But we're holding our breath. So it's not going anywhere. That CO2 is staying in our lungs until we exhale, but we're underwater. So you have a high heart rate, high respiration rate, because your body, your brain is like, uh-oh, this is not good. This is not good at all. We're about to die, right? We're not about to die, but we are at risk of dying. So immediately, when you get your head out of the water, you start breathing fast. You're like, right, hyperventilating. And you have a high heart rate because you're trying to get that CO2 out of your body. So the same thing with low O2, okay? If you have a low O2, we want to hyperventilate so we can get more oxygen into our lungs. So this high CO2, low O2 happens at the same time. If you have high CO2, you must have low O2. And vice versa. If you have high O2, you have a low CO2 level. Oh, by the way, high oxygen is also bad. Because you can have a higher pH blood, and that's a whole different story. So next time, if you were to go in an ocean or into a pool and you hold your breath for a minute, notice your heart rate and respiration rate. And now you will know it's due to chemoreceptors that causes that high heart rate and respiration rate. If you found this video helpful, please like and subscribe. And until next time, later.